So hi guys, I'm Shubham Agrawal and in today's session we are going to study about trees. Okay, so let me see whether am I audible and clearly visible or not. One second. Yeah, I think I'm clearly audible and visible. Okay, so let's start. So in today's session we are going to study about trees. So as you can see, trees are very important from great point of view because there is at least one question that comes from this area. Okay, so it can be from traversal. Okay, it can be on BST, binary search tree, or AVL tree. Okay, or it can be on number of nodes, height of the tree, or something like that. Okay, so it is very important to study this topic. Okay, so now let's see what is our today's agenda. So this is our today's agenda. First, we are going to see what is tree, then trees terminology, then what is binary tree, structure of the tree, traversal technique, in order, pre-order, post-order. Then we will see binary search tree. Okay, insertion in BST, deletion in BST. Then we will see some applications of tree, and after that we will do some gate questions. Okay, so this is our today's agenda. Now let's see. So tree is a non-linear data structure. Okay, so we have data structures. Okay, and we have studied so far linear data structure. Okay, so we have studied linear data structure in which we have studied array, stacks, queue, and then linked list. Okay, and in non-linear data structure we have tree, graph. Okay, so these are the two data structure that we have in our non-linear data structure, in which in this session we are going to study about tree. Okay, and in the latest session we are going to study about graph. Okay, and we have already studied arrays, stacks, and queues, and linked list. Okay, so tree is a non-linear data structure, so that the nodes that are there means they are not in sequential order, they are in some non-linear fashion. Okay, so a node can be connected to two or more nodes. Okay, so if it is a root node of a tree, so I will tell you what is a root node. But first of all, let's see if it is a node, root node, and then it can have two or more children. Okay, so it can have four children. But in linear data structure, if we have a node, then we can have a next node or we can have a previous node. So we have the nodes in sequential order. But in tree, this is not the case. In this, we have a non-sequential order. Okay, and it is something like a hierarchical data structure. Okay, so it is something like this. A hierarchy is formed here. Okay, so it is tree. Okay, and we can also define tree as a connected graph with n nodes and n minus 1 edges and with no cycle. So in tree there is no cycle. Okay, so let me just draw a simple tree. Okay, so let's take an example of a tree. So here we have, so this is the example of a tree in which we have the root node. Okay, and so we are going to traverse the tree from the root node. Okay, so in linked list we have something like, in linked list we have something like head. In tree we have root node. Okay, so okay, so as you can see, if there are 1 2 3 4 5 6 7 and 8, so 8 nodes are there. So if we count the number of edges, so it should be 7. So 1 2 3 4 5 6 7. So 7 edges are there, and as you can see here, there is no cycle. So cycle is something like this. So here it is a closed path, so it is a cycle. So but in tree there is no cycle. Okay, so this is about the basic of tree. Okay, so we will study of graph. What is a connected graph? So connected means from every node there exists a path to every other node. Okay, as you can see from here, I can go to this node using this edge, this edge. Okay, so there is a path defined here, so I can move from this node to this node. So in tree, every node has a path to every other node. Okay, yeah. So this is about a tree, and let me just classify tree. Okay, so if a tree has two children, then it is a binary tree. If a tree is a tree has three children, okay, two children, then it is a binary tree. Okay, so here a node can have only two children. Then we have three children, and in this the tree is ternary tree. Okay, in which a root node has three children, can have three children. It can have less also. Okay, and if we have n childrens, okay, then it's called an array tree. Okay, an array tree. So here there are n childrens. Okay, yeah. So this is about binary tree, ternary tree, and n-ary tree. Okay, now let's see some terminology related to tree. Okay, so these are the some terminologies that are related to tree. First is root. So as you can see, if I draw a tree, so 1 second, yeah, 1 second. Yeah, so sorry for that. Okay, so we have root node. Okay, so suppose this is the tree. Okay, suppose this is a tree. Okay, so in this the topmost node is called root node. Okay, so in this tree if we see, so here this node is our root node. Okay, and uh, for this root, this node and this node is the child node. Okay, so if we have a node, then the child node of this node will be this and this. Okay, then we have parent node. So if we consider this node, then its parent would be this node. Okay, so let me give some names to these nodes. Okay, so it will be easy for to understand. A, B, C, D, E, F, G, H, I. Okay, so if I talk about G, then G has E as a parent. Okay, so parent of, if I do parent of G, so it should give me E, because parent of G is E. Okay, and child of E, then it will be G and H. Okay, now what are siblings? So node with the same parents are known as siblings. So here B, C, D are siblings. Okay, because they have the same parent, that is A. And here G, H are the siblings because they have common parent E. Okay, then we have leaf nodes. So leaf nodes are the external nodes, means they are the last node in the tree. So here as you can see in this leaf node there is no left children and there is no right child. Okay, so it is a leaf node. Here D is also a leaf node, so it is a leaf node, it is a leaf node. Here it is a leaf node, it is leaf node. I is also a leaf node. Okay, so as you can see, they have no child. Leaf node have no child. no children. Okay. Then we have non-leaf nodes. Non-leaf nodes are also known as internal nodes. Okay. So we have C as an internal node. Okay. So let me write it non-leaf. So C is non-leaf, E is non-leaf, F is non-leaf, and root node is also considered as a non-leaf node because it has it is an internal node. Okay. So here A, C, E, F are non-leaf node, and B, D, G, H, I are the leaf node. Okay. Now we have ancestors. So if we talk about this node E, okay, so the ancestor of E will be the nodes above E. So the ancestor of E will be C, D, A. Okay, means ancestor of node E will be C and A. Sorry, B and D will not be the ancestor. So they should be the uppermost node which is connected to E. Okay, so E has C and A as an ancestor. Then we have descendants. So here E has the descendant G and H. Okay, so nodes below E are the descendant of E, and nodes above E are the ancestors of E. Okay, and then we have age. So age is this: the link which connect two nodes are known as edge. Okay, link which connect two nodes. Then we have level. So if we consider a tree, so here I have drawn a tree. So as you can see, this is our root node, and root node is at level 0. Okay, then the level below it will be level 1, and after that the level will be level 2, then level 3, then level 4. Okay, so as you can see, 0th level root node is at 0th level. Other nodes means after the root node we have the internal nodes which are at level 1, level 2, level 3, and level 4 respectively. Okay, so this is about the level. So in tree, root node is at level 0. Okay, now let's see some more terminology related to trees. Okay, so first one is depth of the node. Okay, so if I have a tree something like this, so if I want to find the depth of this tree, this node, okay, so the depth of the node is defined as the length of the path from the root to the node. So root to node. So root is this. Okay, so the path length is 1, 2. So the depth of this node, suppose it is A, B, C, D, E, and F. So the path between so the depth of D is 2, because from root to D there is a distance of 2. Okay, and height of the node is defined as the distance from node to leaf. So from node to leaf, so here D and leaf is F, so the distance between D to F will be, so if I define height, so height of D will be 1, because the path length is from D to F is 1. Okay, yeah. So if we talk about depth, then we have to compute the path from root, and if we talk about height, then we have to compute the length from leaf node. Okay, leaf node. Now let's talk about the height of the tree. So the height of the tree is defined as the height of its root. Okay, so as you can see, the distance from leaf to root is 1, 2, 3. So the height of this tree is 3. And what is the depth of this tree? So depth of the tree is also the length from root to leaf. Okay, and it should be the highest depth. Means uh, if, because here E is also a leaf node. Okay, and here F is also a leaf node, but the path length from A to F is 1, 2, 3, and from A to E is 2. Okay, so here it is 3 and here it is 2. So we have to take the maximum of those. Okay, so depth of the tree is defined as the maximum depth of the tree. Okay, maximum depth of all the nodes. Okay, so in this case also the depth is from root to F we have 3. So depth of the tree is 3, and height of the tree is also 3, because from the leaf to root we have the distance of 3. Okay, so height of the tree is the height of its root. Okay, and depth of the tree is the maximum of maximum depth of all the nodes. Okay, then we have node degree. So node degree can be defined as the maximum number of children a node can have. Okay, a node can have. So here, as you can see, the depth of the C, the node degree of the C is 2 because it has 2 children. Okay, and what is the degree of tree? So degree of tree is the maximum number of node degrees. Okay, so we have, if we talk about depth of this tree, okay, so it will be the so here the degree of f is 1, degree of d is 1, degree of e is 1, degree of c is 2, degree of a is also 2, and degree of b is 0. Okay, so the maximum of all the degrees will be 2. So the degree of this tree is 2. Okay, yeah. So this is about the depth, height, and node, depth, height, and degree. Okay. Now let's see what are binary trees. So we know that binary trees are the trees in which a node can have at most 2 children. At most 2 children means it can have 0, it can have 1, or it can have 2. Okay. So children. So let's consider this tree. So we have a node here, as you can see. Um, okay. So I have this tree. Okay, and it is the root node. Okay, root is pointing to the this node. Then we have, so each node, as you can see here, a has two children, b has also two children, c has one children. Okay, and then d also has one children, e. Okay, then e also has one child, that is f. Okay, and here it is g, h, I. Okay, so here g has no children, and h and I has so h has 1 and I has 0. Okay, 0 childs. So here it is a binary tree because because uh, every node has at most 2 children. Okay, so it is a binary tree. Now let's talk about strictly binary tree, or it is also known as full binary tree. So in this, a node can have 0 or 2 children. So if I draw a tree like this, in which I have a tree in which nodes are there, and each node can have either 2 children or can have 0 children. So as you can see here, in this node, in this tree, we have A has 2 childs, B has 2 childs, D has 2 childs, C has no child, F has no child, G has no child, and E also has no childs. So here each node has either 0 childs or either 2 childs. Okay, so it is an example for full binary tree or strictly binary tree. Okay, and it is the example of binary tree in which any node can have 0, 1, or 2 children. Okay, now let's see what is complete binary tree. Okay, so complete binary tree is defined as the binary tree in which the second last level is completely filled, and the last level may be filled or may not be filled, but the filling should be done from left to right. Okay, so let's see what is complete binary tree. So if I have a tree something like this, okay, in which the second last level, so here the second last level is this. So here the second last level is full, and the last level contains 2 nodes. So here it is the example of complete binary tree. So here if it is something like this, if the node is come here, so it is not an example of complete binary tree. So because the filling should be done from left to right, because here this node has no children and this node has the children, so here it will be wrong. Okay, so this is the definition for complete binary tree, and in some textbook complete binary tree is defined as a perfect binary tree. So it is means some author define complete binary tree as a perfect binary tree, and some of author define complete binary tree as this. Okay, so we have to follow this. Complete binary tree means the last level may or may not be filled, but the bottom level is filled left to right. Okay, and perfect binary tree, so in this, so last level should be full, and so this is the example of perfect binary tree in which we have each level has full nodes, means any so each level has 0, 2, and the last level is also full. Okay, and if we have uh, depth of 3, so here depth is 3, 0, 1, 2, and 3. So in this tree depth is 3, and the number of nodes at the last level are 2 to the power d. So it is 2 to the power 3, that is 8. Okay, so this is a formula to compute the number of nodes in the last level of a perfect binary tree. So a perfect binary tree has 2 to the power d nodes at depth d. Okay, and okay, so this is about the complete binary tree, in which the second last level should be fully filled and the last level may or may not be filled, but the filling should be done from left to right. Okay, so I can't have any node here. Okay, it should be done from left to right. So first left child will be there, then the right child will be there. Okay, and in perfect binary tree at the last level all the nodes should be filled. Okay, yeah. Now let's see uh, things like maximum number of nodes at depth d. So if we have a binary tree, so suppose that we have a binary tree here. Here the depth of the tree is 0, 1, 2. So depth is 2. Okay, so maximum number of nodes at depth d in a binary tree is 2 to the power d. Okay, so why it is 2 to the power d? So at 0th level we can have at most one node. At first level we can have 2 to the power 1 nodes. At second level we can have maximum 2 to the power 2 nodes. If we have a tree with depth 3, so here it would be maximum at the last level we can have 2 to the power 3 nodes. Okay, so at level 3. Okay, so the maximum number of nodes at depth d in a binary tree is 2 to the power d. Okay, now the maximum number of nodes in a binary tree with depth d. So we have to find the number of nodes. So we have this binary tree. Okay, and depth of this binary tree is 3. Okay, and we want to find the total number of nodes in the tree. So we know that at 0th level it is 2 to the power 0 nodes. At first level it is 2 to the power 1 node. At second level it is 2 to the power 2 nodes. At third level it is 2 to the power 3 nodes. Okay, so if we sum all this, so 2 to the power 3 plus 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3. Okay, and if we compute the result, so it will be, so here it is a gp, and the sum of gp is defined as this. So if we have a gp and sum is defined as a r to the power n minus 1 upon r minus 1. If so it starts with, okay, if there are n elements. Okay, so here it will be so a here is 2 to the power 0, that is 1, and the common ratio is, so r is the common ratio, and here common ratio is 2, so it is 2 minus 1, and here it is 1 to n terms should be there, and here 0 to 3 are there, so it will be 4 terms are there, so 4 minus 1 it is 3, so it will be 3 minus 1. Okay, and r is 2, so it will be, so it should be 1 second, it should be n, I think, yeah. So it should be n, and it will be 4, and it will be 16, 15. Okay, so here the answer will be 15. So if we have so n, okay, so we have, if we have a gp something like this, a plus a r plus a r square plus up to a r n minus 1. So the sum of this would be this. Okay, so here r minus 1 is there, so here r minus 1, n minus 1 is 3, so n minus 1 is 3, so n should be 4. Okay, so here the answer is 15. Okay, so the number of nodes in this tree will be 15. So 1 2 3 4 5 6 7 8 9 10 11 12 13 14 and 15. So 15 nodes are there in this tree. Okay, so the maximum number of nodes in a binary tree at depth d will be so if we generalize this, so if we have depth up to 2 to the power d, so it will be 2 to the power d plus 1. Okay, and it will be 2 to the power d plus 1 minus 1. So this will be the generalized result. Okay, so let me write it here. One second. Yeah, so the generalized result is 2 to the power d plus 1 minus 1. Okay, so this is the result, and the minimum number of nodes in a binary tree with depth d will be, so if it is a binary tree and each level we have only one node, so at the d level, so it is 0, it is 1, it is 2, and up to d level. So the number of nodes will be d plus 1. So these are the minimum number of nodes in a binary tree with depth d. So since it is, we have asked for minimum, so we will consider only one node. So because one node should be present so that it can be considered as a level. Okay, because if there are no nodes, then we will not go down. Okay, yeah. So here, if depth is d, then the minimum number of nodes that we can have is 0 to d, that is d plus 1. Okay, now let's see what is the structure of the binary tree. Okay, so we have defined 1 second. Yeah, so let me see the chat also, so there are no questions. Okay, so here structure of binary tree is there, and it can be defined as something like this, in which we have a data field, then we have the pointer to the left, then pointer to the right. Okay, so in linked list we have data and next pointer. Okay, because in linked list the data is stored sequentially, as you can see. Okay, but in tree data is stored in hierarchical manner. Okay, and here it is head. Okay, but in tree we have a root node. Okay, and a root node has data and it has the pointer to left and right node. Okay, so here it is a tree. Okay, and we have data and left and right. So we have two pointers, left and right. Okay, so it is linked list and it is tree. Okay, and initially if it is an empty tree, then root is null. Okay, and we can create a node using malloc function, as we have studied when we have studied dynamic memory allocation. Okay, so this is the basic structure of tree, in which we have data element, then we have pointer to the left and pointer to the right. Since a binary tree can have at most two children, so at most two children, so left can be null, right can be null, left can be null, right cannot, right is not null, left is not. So there will be four cases. Okay, so left and right, there will be four cases. So left can be null, right can be null, so left can be null, and right is not null. Okay, so it is not null. Okay, then it is left can be not null and right is null, and we have both can be not null. Okay, okay, so here we have two children, here we have one children, here we have one children, and here we have zero children. Okay, so here at most any node can has at most two childrens. Okay, 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 so this is the structure of binary tree. Now let's see how we can traverse the tree. So if I have given a binary tree, so I want to visit every node. Okay, so how can I do that? So that for that we have tree traversal techniques. Okay, so if I have a binary tree something like this, and I want to traverse this tree. Okay, so I have three techniques in which I can do that. First is in order, second is pre-order, and third is post order. In order, we visit first left subtree. Okay, then we visit root, then we visit right subtree. In pre-order, we visit first root, then left subtree, then right subtree. Okay, and in post order, root is visited at the last. So first we visit left subtree, then right subtree, and then root. Okay, so this is the basics of the traversal techniques that we are going to use, and this traversal technique can be easily implemented using recursion. Okay, so we are going to see the code for this. So we are going to use recursion to traverse this tree. Okay, so if we have given a binary tree, then how can we traverse? So let's see them one by one. Okay, so let's first see Inorder Traversal. Okay, so in Inorder Traversal, let's consider one example. So we have 1, 2, 3, 4. So it is a binary tree. Okay, so it is a binary tree, not a binary search tree. Okay, so it is binary tree. So let's consider this binary tree, and root is pointing to this, and the node in which value is there, so it is the data item for that node. Okay, and this is the code to traverse the in order. Okay, so here we pass root, and if root is null, then we just return from here. Okay, so here as you can see, first we are visiting the left subtree, so we are recursively visiting left subtree. Okay, then we are printing the then we are printing the data item, and then we are again recursively visiting the right subtree. So here the code for recursion is very easy. So we had to just give this base condition. So this is our base condition. So our base condition is if it is null, then we just return from this code. Okay. So let's try to apply this code on this tree. Okay. So in order, in order, we first go to root. So here we have gone to root. Root is not equal to null, so we will not go to this if condition. Then we will go to in order of left. So first in, so let me write here. Okay, so in order of 1 is called. Okay, and now from in order of 1 we are going to roots left. So root left is in order of 2. Okay, so and again when root is not equal to null, again we will go to in order of left, so it will be in order of 3, sorry, in order of 4. So because left of 2 is 4. Okay, so now when we call this in order with 4, and 4 is not equal to null, then in order of root of left will be called. So here if there is no node, then there is null present here. Okay, so when in order of null is called, okay, so when in order of null is called, then we will just return from there. So here it will be, we will return from here, and first, so here from null is called. Okay, and here we will first print the roots data. So roots data is 4, so 4 will be printed. So let me print the output here. So 4 will be printed. Okay, and then we will call again in order of null. So in order of null, so it is null, so we will just return. Now when this function call is completed, we will again go to in order of 2. Now in order of 2, we are printing first the data. So here the data is printed, so first 2 will be printed, so 4 2. Okay, and then in order of right will be called. Okay, so in order of right, which is 5. Again null will be called, so it will just return from there. Again 5 will print, so 5 will be printed, and again it was called for null, so again it will return, and we will again go to in order of 2. Now we will call in order of so first we will print the data. So here data 1 will be printed, and then in order of 3 is called. Okay, and in order of 3 will call null, and then it will print data. So 3 will be printed, and then it will call null, so null will be there. Okay, so this will be the output of our code. So 4 2 5 1 3. Okay, so this is the in order traversal of this tree. So we have visited the tree in order. Okay, so first we have visited the left subtree, then we have visited printed the data, and then we have visited the right subtree. Okay, now let's see the pre-order traversal. Okay, so let's consider the same tree. Okay, so we have 1, 2, 3, 4, 5, and here we are going to print the output. In pre-order, first we print the data, okay, and then we recurse for left subtree, and then we recurse for right subtree. Okay, so let me just denote pre-order by 3. Okay, so we will call for pre of 1. Pre of 1 will call, first it will print data, so 1 will be printed, so our output will be 1. Then it will call for pre of left, so pre of left is 2. Okay, and when pre of 2 is called, so again it will first print the data, so 2 will be printed, and pre of left will be called, so pre of left is 4. Okay, so 4 will be called. Now again 4's data will be printed, so 4 data is printed. Now pre of null will be called, so pre of null is so null root is equal to null, so we will just return from there. So we will just return from here. So pre of null will be called, and we will just return from here. Okay, yeah, and in C, null value is 0. Okay, so you can write 0 instead of null also. Okay, so here when this function call gets completed, we will go to pre of 2, and in pre of 2, pre of left is completed. Now we will do pre-order of right subtree. So here pre of 5 will be called, and 5 will be printed, and then the call for null will happen. So here it will just do nothing, and it will return. And here when we this pre of 2 is completed, now we will recurse the right subtree of this tree, so it will be pre of 3. So when pre of 3 will be called, so it will print 3, and it will call for its children, so that its children is null, so nothing will happen, and it will just return. So when after this pre call to pre of 1 will be completed, and the output will be this. So 1, 2, 4, 5, 3. So this is our output. So in pre-order there is one thing, that here the first value will be the root value. Okay, and okay, in the output the first value will be the root value. Okay, yeah. Now let's see, 1 second. Yeah, now let's see next traversal technique, that is post order. Okay, yeah, so for that. Okay, so now we are going to study about post order. Okay. So in post order, we first visit the left subtree, then we visit the right subtree, and then we visit the root data. Okay, so let's take an example: 1, 2, 3, 4, and 5. So in this example, we have this subtree, and here when we try to traverse it, so first we will call for post of 1, and it will call for post of 2. Okay, then post of 2 will call for post of 4, and after this post of 4 will call for its left child, so left child of 4 is null, so it is null, so it will just return from here. Again post of right child will be called, so 4 right child is null, so again it will return, and then it will print the result. So here the output will be 4. Okay, and then we will go to post of 2. In this, right subtree is called, so first post of 5 will be called, then it will call for post of null, because 5 left child is null and 5 right child is also null. Then we will just print the result, so here 5 will be printed now. And then we will again go to post of 2. Now left subtree is visited, right subtree is visited. Now the root data will be printed, so 2 will be printed, so 2 will be printed here. Now we will go to post of 1. So left subtree of 1 is visited. Now we will see left subtree of right subtree of 1. So it will call for post of 3. So it will call for null, and then it will call for null because the left and right child of 3 is null. Then it will print the data of 3. So here 3 will be printed. Now post of 1 will be called. We will again control go to post of 1, and since we have traveled left subtree and right subtree, so we will just now print it, print the value, that is root of data. So it will be 1. So in post order traversal, the root will be present at the last. Okay. Yeah. So now let's see what is binary search tree. Okay. So it is very important topic. So here in binary tree we have at most 2 children in binary tree. Okay. And in binary search tree, so it is a binary tree only, but with the following properties. So it has some property that the left subtree of a node contains only nodes with the keys lesser than the nodes key. So if left subtree is present for this node and its value is 50, so the nodes present in the left subtree should be less than 50. Okay, it should be less than 50. And in the right subtree, the node contains only the keys with greater than the value of the node keys. So in the so if it is a left subtree, so left subtrees node contain less than 50, and here it is a right subtree. So here every node in the right subtree should contain the key which is greater than 50. Okay. So here it should be 60, 80, 55, and it can be 45, and it can be 10, and it can be 50. So it can be 49. Okay. Yeah. So here all the values are less than 50, and here all the values are greater than 50. And the third condition is that left and right subtree each must also be a binary search tree. So it should be recursive, means every node should follow this property. So here we have satisfied the property for 50. Now let's see for 45 it is satisfied or not. So here 10 is less than 45, so it is correct, and 49 is greater than 45, so it is also correct. And here also 60 should follow these properties, left subtree and right subtree. So here 55 is less than 60 and 80 is greater than 60. So yeah, it is a valid BST in which a node in the left subtree all the nodes are less than the root node value, and in the right subtree all the nodes have the greater value than the root node. Okay. So this is the basic of binary search tree. Okay. So what is the benefit of this binary search tree? So if we do this, then we can in average time we can search an element in, so it is in average time we can search an element in log n time. If n nodes are there, then we can search in log n time, and in the worst case it will be order n time, because in worst case it will be a skew tree in which we have only nodes in one direction, means at each level only one node is present. Okay, so we will see about them. So first let's see how we can insert a node in a binary tree, binary search tree, insertion in BST. Okay, so if we have some nodes, so let's say 5, 10, so 5, 8, 10, 2, 3, and 12 and 13. So I have to insert this nodes in the binary search tree which is currently null. So root is currently pointing to null. Okay, so root is currently pointing to null, and there is, means the tree is empty. Okay, so let's see. So this is the insertion algorithm. Okay, so it is a recursive algorithm because here we are calling insert again. Okay, so let's see how this algorithm works. Okay, if so first we will pass root. So root is null and the key is 5. So if root is null, then we will create a node. Okay, so a node will be created, and in this the root data will be key. So key is 5, so 5 is there, and in left and right there will be null. Okay, now when we insert 8, so here root is not null, again the root is passed, so root is not null now. Okay, So roots data will be compared. So roots data is 5. 5 is less than key because 8 it is 8. So we will go to the uh, so root data is less than key. Okay. So here it is 5 and sorry. Okay. So root data is 5 and key is 8. Okay. So key should be inserted at the right side. So it should be greater than here. Okay. So here the symbol should be greater. So if roots data is greater than key, okay, then we will come to this condition. Else we will go to this condition. So here 5 is not greater than 8. So we will go to the right. Okay. So here insert of right will be called. Okay. And in the right we will so here right is null. Okay. So here root is equal to null. So we will allocate one node. Okay. So here link is not present right now. So 8 will be there and its child will be null. Okay. So null will be there here. And now when we return after creating this function, so we will return the root. So after this root of right, so in this we will create the link because previously 5 was pointing to null, right of 5 is pointing to null. Now it will point to the result returned by this insert function. Okay, so it will be 8. Okay, so now 5 will point to 8. So let me remove this, and after this we will return root. So it will be 5. So now root will point to this 5. Okay, and we have inserted two elements here, 5 and 8. Now let's insert 10. When 10 is inserted, so 10 root data is 5, 10 is not greater than 5 at 5. Okay, so means 5 is not greater than 10, so it is false. So we will go to root of right. Again, root of right we have 8. Now 8 is compared with 10, so it is also greater. So we will go to the right here and 10 will be inserted here. Now when we insert 2, so 2 is less than 5, so 2 will come here and we will insert it here. Then 3, so 3 will come here, 5, 2 and 3. Then we have 12, so 12 will come at the last. Okay, so 12 will be here. And then we have 13, so 13 will come at the right of 12, so it will be 13. So in this way the insertion works. Okay, in BST. So here we have inserted some elements from so here we have inserted 5, 8, 10, 2, 3, 12, 13. Okay. Now let's see how we can search an element in a BST. So let's suppose we have a BST. Okay. And here some elements are there, 20, 20, 15 and 25 and 35. And here 21 is there. Okay. So it is a BST because each node in the left, it has less keys. Okay. So value of the keys are less than the root node, and here all the values are greater than, and this property is followed at each node. Okay. Now let's see how can we search in this PST. Okay. So let's suppose I want to search 25. So I will call this search function, and if it is a root equal to null, so it will return 0. So it means search is unsuccessful. If it returns 1, then search is successful. So root data is compared with key. So root data is not equal to key because it is 10. So we are currently here. So it is 10. So we will compare root data with key. So key here is root data is 10. Okay. So root data is 10 and key is 25. Sorry. Yeah, key is 25. So 10 is less than 10 is greater than 25. Okay. So we will go to the right of the tree. So we will come here, and again 20 will be compared with 25, and again we will come here right of it. Then 25, when we compare it with key, so it is equal to key, so it will return 1. Okay, and this 1 will be returned recursively to the previous function, and at last when we get the result from this function, it will be 1. So it is a successful search. So 1 means successful search, and then 0 means unsuccessful. Okay. So here 25 was present, hence the result is 1. So if we search for 4, okay, so if I want to search for 4, okay, so 4 is not present in this. So let's say key is 4, then 4 is not so let me write it here, key is 4, then 4 is compared with 10, so 10 is less than 4, so it is false. So we will go to the left, and and then we will compare 5 with 4, so it is also not correct. So again we will go to the left of 5, so it is null, so 0 will be returned. So for key equal to 4, 0 will be returned, so it is an unsuccessful search. So in this way we can search in a binary search tree, and to search an element in a binary search tree, it takes log n time in average case, but in worst case it can be order of n time. Okay, so please remember this point, it is very important. Now let's see how we can delete a node in a binary search tree, binary tree. Okay, so if we have a binary tree, okay, so first let's see the algorithm. So in this we have three possibilities. A node to be deleted is a leaf. So if it is a leaf, then we will simply remove it from the tree. And if the node to be deleted has only one child, then we will copy the child to the node and delete the child. And this third case is a little bit complicated, in which if it has two children, then we have to find the in order successor. Okay, so let's suppose that I have a 12 and 13 and 11. So here if in this tree the in order successor of 10, what it will be? So it will be 11, because after 10 11 should be there. Okay, if we just means if we consider it in a sorted order, and it should be 11. Means sorted order means if we take the in order of this, so in order of BST, so there is one more point. In order of BST is always sorted. Okay, the result is sorted. Okay, so it is an important point. So here if we find the in order of this, so if we do the in order traversal, and after 10 it is 11, so in order successor of 10 is 11. Okay, here, so we first find the in order successor of the node, copy the content into the in order successor of the node, and then delete the in order successor. Okay, so here also the deletion algorithm works in a recursive way, and we can also consider the in order predecessor also. So we can use either in order successor, or we can use in order predecessor. Okay, predecessor. Okay, so it is up to us. So here we are going to use in order successor for this. Okay, now let's see an example. So let's suppose this is the example, and I want to delete 76 from it. So 76 is present here, so it is a leaf node because it has no right child and no left child. Okay, so no left and no right child. So here I can simply delete it from the tree. Okay, so I can simply delete it from the tree. Okay, now if I want to delete 32, okay, so here 32 has a child 28. Okay, so it is a single child, so I will just copy the value, so it will be 28 and it will be 32, and I will delete this 32. Okay, so here our tree will look like after this two operation, 17, and here 28 will be there, and here 88, 65, 97, 54, and then 82. Okay, now if I want to delete 88, so 88 has two childs. Okay, so it is 65. Okay, so 88 has two children, so 65 and 97. So here I have to consider the in order successor of 88. So in order successor of 88 is 97. Okay, so we will copy 88 here, and we will copy 97 here, and we will delete this 88. So now it is a leaf node, so we can simply delete it. So in this way the deletion will work in BST. So we have deleted 76, 32, and 88 from this. Okay, this binary tree. Okay, so now our new tree looks like this. 32 is deleted, 76 is deleted, and 88 is deleted. Okay, now let's see our deletion code. So this is the code for deletion, in which we have a delete function. If it is a root, then we will just return it. If it is a null, then we will just return. After that we will compare the data with the root node. If it is less than, if root data is greater than key, then we will delete from left, otherwise we will delete from right. Okay, and here is our main conditions. So if both are both the child are null, so it is a node with no children, so it is a leaf node. So we will simply delete it, return null. Okay, and if it has only one children, then we will copy that children and free the node, and after that we will return that node. Similarly for the right child also, and this is the case in which we first find the minimum value node in the right subtree. So minimum value node in the right subtree will be our in-order successor. So okay, so it will be our in-order successor. So here we will search for the minimum node in the right subtree of the node that we have to delete. Okay, and then we will just copy the data and we will delete that in-order successor. So this is the simple code for the deletion in BST. Okay, and in this way we can delete it. Okay, now let's see some applications of tree. Okay, so tree can be used in file system. So trees are used in file system because in file system we have hierarchical structure. So we have something like this. We have root folder. Okay, and in that root folder we have home, and that in home we have our my document folder. Then we have my downloads and other things. Okay, and yeah, so here it is forming some tree like structure, and here some user2 is there, and in this way our file system is there. Okay, so here it is, each node is a directory. Okay, and it can be a file also. Okay, so file will be our if it is a file, then it will be our leaf node, because file cannot have any other directory. Okay, it will be our leaf node. So here the in file system data is stored in a hierarchical way. Okay, then trees are used in trie data structure, which can be efficiently used to retrieve information. So we will study about trie, okay, in the later lectures. Then we have balanced BST like AVL tree, red black tree, in which the searching in the worst case is log n time. So here we perform some rotation and some other properties are there. So by using that, we reduce our complexity from first case of order n to log n. Okay. Then we have B tree and B plus tree. So in B tree and B plus tree are used in database. Okay. So they are used to store the data in the database in the hard disk, means secondary storage, and it is in B tree. It is a M way B tree, means M way tree, in which order of B tree is M. Okay, so it means that it can have at most M childrens in the B tree. Okay, so it can have M children and M minus 1 keys if order of a B tree is M. Okay, so this is about the B tree and B plus tree. So trees are almost used everywhere in computer science. Okay, yeah. Now let's do one gate question. So this question was asked in gate 2020, in which we have given the pre-order traversal of the binary search tree, and this is the pre-order, and we have asked which one of is the post-order traversal of the tree. And to construct a binary search tree, we need at least in-order traversal and pre-order traversal to construct a binary tree, or we need in-order traversal or post-order traversal. Okay, but since here only pre-order is given, in order is not given, but we know the property of binary search tree in that is in order the elements are sorted. So we just need to sort this element. So here 10, 11, 12, 15, 16, then we have 18, 19 and 20. So this will be our in order traversal for this tree. Okay, and this is our pre-order traversal. So if we know in order and pre-order, then we can construct our tree. Okay, so now let's construct our tree. So since we know that in pre-order the first element is root, so we know that 15 will be our root. Okay, now we will search 15 in our in order. So in order in 15 is 15 is present here, and in the left of 15, 10, 11, 12 is there. So here it can be 10, 11, 12 in the left subtree, and in the right subtree it can be 16, 18, 19 and 20. Now let's see what result will be there here. So here after 15 there is 10. So here 10 will be there and 10 is present here. So 10 has no left child and 10 has two right child. So here we have 10 and here there will be no node. Here 11 and 12 can be there. And now which one of will be there? So here 12 is present first in pre-order, so 12 will be there here. Okay, and after that after 12 it is present in the left of 11, so it will be here, and we have considered 11. Now this left subtree is completed. Now let's see the right subtree. In right subtree after 11 it is 20, so 20 will be here. Okay, and 20, so we will search 20, and in left of 20 16 18 19 is there, and right in the right there is no element, so in the right subtree of 20 nothing will be present. So the 16 18 and 19 will be present here. Okay, and the next element will be 18, so 18 will be here. So since it is coming in pre-order, so 18 will be there, and in 18 is here, so left of 18 is 16 and then 19 is there, so 16 will come here and 19 will come here. Okay, so this will be our tree. Okay, now let's find the post order traversal of this tree. So in post order traversal we have left, right, and then root. Okay, so first we will go to the left subtree, so it is 11. Then we will go to right, so right is null. Then it is root, it is 12. Then we will go to 10, so 10 will be there. Then we will go to again left of it, so it will be 16, and then we will go to 19. Then it will be 18, and after this it will be 20 and 20. Finally we will visit our root, that is 15. Okay, so we will first see left, then right is null, then we will see root, then we will see root, then we will go to again left, right, root, right, root, and root at last. Okay, so this will be our result. So the correct answer for this will be B. So here 11 12 10 16 19 18 20 15 will be your answer. Okay, so this is the post order traversal of our tree, and it is matching with our answer. Okay, now let's do one more question. So in this question the post order traversal of a tree is given and in order is also given. Okay, so it is a binary tree, not a binary search tree, so the property of in order is not followed here. Okay, so here the elements will be not sorted if we do the in order traversal. So here 8 9 6 7 4 5 2 3 1, so it is our post order. And then 8 6 9 4 7 2 5 1 and 3. Okay, so it is our in order. Okay, now the height of a tree is the length of the longest path from root to any leaf. So they have defined height something like this. Okay, and so any leaf to root, so we have to compute the path. So first we know the tree for that. Okay, so height of the binary tree they have asked, so first we have to compute the tree for this. So we know that if post order and in order is given, then we can construct the tree. Okay, so let's construct the tree. Since it is a post order, so we will start from the right. If it is a pre-order, then we have started from the left. So because if we know that in post order the rightmost element will be our root. Okay, so here you can see that one will be our root, so one will be here, and we will search one in our in order traversal. So in order traversal, in the left of one this much elements are there, and 3 is in the right. So in the right, so 3 will come in the right. Okay, so here 3 will be there, and after that we want to so here 8 6 9 4 7 2 5 1 can be there. Okay, so we want to know which of one of will be there, so we will consider post order. In this 2 is there, so 2 will be present here. Okay, and now we will see here. So here in the right of the in the left of the 2 8 6 9 4 7 is there, and in right only 5 is there, so 5 will be here. And then we have after 5 we have 4, so here we will have in left 4. Okay, now left of 4 is this and right is this, so 7 will be here, and here after 7 we have 6, so 6 will be our left child of 4, and since 6 has 8 as a left child and 9 as a right child, so it will be 8 and it will be 9. So as you can see here, it is 0th level, it is once first, it is second, it is third, and it is 4th level. So here the height of our tree is 4. So the correct answer is 4. Okay, so we have construct our tree with the help of post order and in order traversal. Okay, now let's do one more question. Okay, so in this we have given the pre-order traversal of a binary search tree. Okay, so we have given the pre-order traversal, so 12, 8, 6, 2, 7, 9, 10, 16, 15, 19, 17, and 20 is there. Okay, now the in order, so it is pre, so in order of this would be the sorted order of this. Okay, so it will be 2, then 6 is the smallest, then 7, then 8, then 9, then 10. Okay, and after 10, 12 is there, after 12, 15 is there, then 16, then 17, then 19, and at last 20 is there. Okay, so this is our in order traversal, and this is our pre-order traversal. So how we have computed in order traversal? So because we know that it is a BST, so the in order traversal will be the sorted order, will be in sorted order. So we just sorted this list. Okay, this traversal. Okay, yeah. Now let's draw the tree. Okay, so here, since it is a pre-order, so we will start from left. So here 12 will be our root node. We will search 12 from here. Okay, so here it will be the right subtree, and it will be the right sub, it will be the left, and it will be the right subtree. Now uh, the left of 12 will be after 12, 8 is there, so it will be 8. Okay, so here 8 will be there, and left of 8 is 2, 6, 7, and 9, 10. Okay, so after 8 it is 6, so 6 will be present here, and 6 has 2 and 7 as the left and right, so 2 will be here, 7 will be here. Okay, now we have done up to 8. Okay, so after 7 it is 9, so 9 will be present here, and in the left of in the right of 9 it will be 10, and left it will be null. Okay, because all the elements are considered already here, and 10 is also done. Now let's construct the left right subtree of our 12 node 12. Okay, so here after 10 it is 16, so 16 will be our right node, and after 16 in the left of it, it is 15, so 15 will be present here, and 17, 19, 20 is in the right, and since after 15 it is 19, so 19 will be here, and 19 left is 17, and it is 20, so it will be 17 and 20. Okay, so it will be our tree, and the post order traversal of this tree will be 2, then 7, since the post order traversal means left, right, and root. Okay, so we will consider it root at the last. So we will first consider the left most node, that is 2, then right 7, then root, that is 6, then we will go to the again at the right, because since there is no left, so it will be 10, then it will be 9, then it will be 8, then we will again go to the left, so it is 15, then 17, then 20, then it will be 19, then it will be 16, and at last it will be 12. So this is our post order traversal of the tree, and the option matching to this is 2, 7. Okay, so 2, 7, 6, 10, 9, 8, 15, 17, 20, 19. Okay, so sorry, here after 19, 16 will be visited, and 20 will be visited after that, so 16 and 20. Okay, yeah, so 12 will be visited at the last in post order traversal. So the correct answer is B. Okay, so this is our correct option, and the post order traversal will be this. So as you can see in the means in the previous gate year papers, there is at least one question from this tree traversal. So you should have a proper understanding of this tree traversal techniques in order, pre-order, and post-order, and you should be able to construct a tree with the help of this traversal techniques. Okay, so this is it for today's session. So thank you for watching. Okay, so yeah, thank you guys.